do you guys have the worksheet I gave you yesterday that we didn't get to? It's called worksheet 4-3. All right, anybody else need a copy? 4-3, that's the one we're doing right now.
You're welcome, Stacy. Yeah.
Yeah. All right, so we've been talking about the fine-tuning of the universe, design in the universe. Okay. Now, this initial fine-tuning, or what we could say is this design or precision that we've noticed in the universe, for many people, it is stronger evidence for the existence of God than even the cosmological argument or anything else. So, we've already talked about Isaac Newton and his belief on this, but let me read to you a quote from him again. It says that this most beautiful system of the sun, planets, and cosmos and comets could only proceed from the counsel and dominion of an intelligent and powerful being. So this is an old argument, it's an old idea, and it's been around for a long time. But it was William Daly, another scientist who lived in the 1700s, who made this argument more famous when he talked about. He said, imagine you're walking through a forest and you happen to look down and see a pocket watch. That's what he talked about. We now say it's more like a watch, okay, like a diamond-studded Rolex. Imagine you're walking through the woods and you see a diamond-studded Rolex in the dirt, okay? What is your first initial assumption about that watch?
We lost it.
You think it's fake?
Because
Because it's too valuable?
Yeah.
Okay. All right. What's your more subconscious assumption?
Let's
Sell it.
It was made with
Tiger keeper.
That's actually true.
Andrew is right. You're not going to assume that it was caused by natural processes, are you? Like, obviously not. You're not going to say, oh, I think, erosion and weather and things like that have caused this.
You just spawn.
Just spawn. Yeah, it's not. We're not going to believe it just spawned out of nowhere. And so this is kind of the metaphor for the design properties of the universe. You look at the universe and you see how complex it is, infinitely more complex than the watch, right? And the idea is, if we can't even jump to a conclusion that a watch would spawn from natural processes and chance, why would we think that the universe, which again is much more complex, why would we think that comes from chance? So this is the metaphor and the idea. But how do we prove that the universe is finely tuned? Like, what kind of evidence do we bring up? Well, a lot of it we've talked about kind of informally.
Gravity.
We have gravity, we have atmosphere, we have all of these different factors. What I'm going to do today is give you a list, okay? It's not an exhaustive list, meaning it's not everything we could talk about. We could spend a whole quarter, a whole semester, a whole year on just these constants, okay? But I'm going to give you 12 that I think are probably the strongest or most important to understand, and that's what you're going to write down on your worksheets here. But I want us to think about all of this as if we're astronauts, okay? So when someone goes in a spaceship into space, that craft that they are in is designed to keep them alive. And there are many things, many factors that have to be considered when you're in a craft like that. So what kinds of things do you have to survive in space?
Gas or fuel.
You need fuel in order to move, otherwise you get stranded. Yeah.
Oxygen.
You need oxygen, okay? Yeah.
Water.
You need water. Food. What else? Electricity.
That thing that filters. They have these things in the spacecrafts that filters
Carbon.
all of the water. So they recycle water.
Yeah, they have to recycle water. That's one of their solutions to keep water,
Oh, they need
Yeah.
other gases, not only oxygen. Because I heard that there was one where they put like purely oxygen and like a spark blew up the whole.
Oh yeah, and we'll talk about that.
You have to have a balance between.
It's not just oxygen. It's the way our atmosphere works. We say, oh, we need oxygen to survive. That's true.
Nitrogen.
But if it were just oxygen in our atmosphere, we would all die. Okay. We need other things as well, nitrogen and so on. So, in fact, on the space shuttles, they actually take hydrogen and oxygen and mix them to make water. It's a very interesting thing. Anything else? What kind of other things do they need to factor in?
Oh, communication.
Yeah, they need communication. Okay. Sorry? Yeah, they need to figure out some way to at least.
Get into the hole so they don't have to waste all the gas.
Yes, they use gravity, the gravity of planets and the moon to travel. Okay, there's a lot of things. The main thing I want us to focus on is what they need in order to survive. Because space is a very hostile place, right? It is not made for humans, you might say.
That's why we weren't there.
That's why we weren't there. That's why we don't have life spawning up anywhere willy-nilly. Okay? Willy-nilly. That's an old phrase. Okay.
Yep.
We need certain things in order for life to exist and survive. Okay? So that's what we're going to call constants, necessary constants. Okay? So this is your first blank on the worksheet here. What is a necessary constant? We're going to call them rules in physics or the universe.
Oh, we're in the
Yeah. Necessary constant is a rule in physics or the universe that is necessary for our survival. And really, you might say for life to exist. Let's say that's better, actually. For life to exist. Okay? A rule in physics and the universe. What did I say? By which it is, which is necessary for life to exist. Okay.
Yes.
Now, all of these, just one of them is a strong and powerful argument for design, as we'll see. But when you combine all of them together, and when we understand that there's actually more than just these 12, then we start to realize, okay, the chances of a universe happening to be this way by chance are very remote. And again, what are the two criteria we look for when we're looking for design? Extreme improbability. And what's the second one?
Recognizable or independently
recognizable pattern of functional requirements.
Functional requirements, recognizable pattern. In other words, individual parts working together for the same function. Okay? We're going to see that in not only in each individual one, but especially when we combine them all. Okay? So let's talk about the first one. We're just going to run through them. Okay? The first three, as you notice on your worksheet, the first three are kind of you're given just an extra blank. Okay? The first three have to do with. Let me put it this way. The first three are dealing with the Big Bang and the expansion, okay? They're dealing with the origin of the universe as atheists and materialists see it. In other words, we're going to follow their thought experiments, and we're going to see the complete unlikelihood that anything that they say happened could happen without a mind behind it, okay? So the first one is the fine-tuning of initial conditions of the universe. Initial conditions of the universe. So think of it this way. You've got, at least the way it's formulated. I need to put this one. That I'm proud of. Okay. See, trashy ball. I told you. All right. Here we go. Can you see me on the camera? Okay, I'm gonna move. got the initial conditions of the universe. When I say initial conditions, what I mean is what physicists speculate would have been there before the initial or the expansion, okay, the explosion. So you've got initial conditions. Can anybody tell me how they, what do they view, what do they say about these initial conditions? You guys hear anything about that?
Nope.
So they'll say something like all of matter was compressed into a single pinprick,
Oh, yeah.
stuff like that, which there's really no basis for because, well, as we talked about, space and time are connected. And the beginning of space is also the beginning of time. So we're talking about a beginning to everything in existence. They're trying to get around that by saying, well, before the explosion, and we'll talk about why this is a problem when we talk about cosmological evidence, but they'll say before the explosion, everything was there, it was just condensed, okay? So the problem is that in order for our universe to be as it is, then those initial conditions would have to be a very particular way. If they were any different, then the universe that came out of the explosion would not be conducive to life. So here's a metaphor. Before we had tunnel boring machines, you know how we made tunnels in like mountains when we were making railroads and so on?
Yeah, we dug it.
We blew it up, actually.
Dynamite.
Yeah, with dynamite. And it was very important that you would have these engineers figuring out how to fine-tune the explosion so that the explosion went correctly
So they did
in
Mount
the
Rushmore.
right direction. No, they didn't blow up Mount Rushmore.
Yeah, they did. They used TNT.
Well, they might have done that initially, but
Yeah.
the cars and faces, no, they didn't use TNT. But anyway, dynamite, right? You have to configure the explosion specifically. And that's the idea here with the universe. If matter was in existence, before the explosion, that matter has to be formulated in an exact way. And the odds of coming out of that with life are astronomically low. And we're going to combine this with the next one, okay? Initial entropy fine-tuning. So, what is an entropy? What is entropy?
It's a measurement of chaos in the universe.
It's the measurement of chaos in the universe. Okay? So, higher entropy means higher chaos. Lower entropy means higher order. Okay? So, we look at the initial conditions before an explosion. And we say there was a certain amount of chaos, a certain amount of entropy at play before the explosion. And again, the number becomes very exact. Where think of it as you have several options coming out of this. Okay. I don't know if you can see this on the screen. Okay, maybe I'll turn on the light real quick. All right. So when it comes to entropy, when it comes to order or disorder, there has to be a certain amount in the initial conditions so that when we come out of the explosion, there's a particular amount. So let's say this range is high order, or I should say high entropy, high disorder. And then over here we have low entropy. So what happens if there's too much entropy?
No energy.
Sorry?
No energy.
There's no energy? Yeah, we run out of energy. Okay, basically everything will be black holes.
Yeah.
Okay. What about low entropy? Too little entropy.
It's going to be more explosions?
Everything just stays like a white hot gas.
Yeah. Something like that.
So
much.
too much order is bad because then you basically have no particles coming together at all.
Yeah.
So you don't have universes. Okay. So here are the two options. Again, if you're talking about an explosion that's unguided, you have a vast amount of options when it comes to high entropy that all lead to death. None of them lead to life. They're all black. The universe is just black holes. And then you have a vast number of options where the universe has no galaxies or anything because there's not enough entropy. Okay? And of course, where we are is here. We have a very perfect amount. Now, a guy named Penrose, he was a compadre of Hawking, Stephen Hawking. He worked with Hawking a lot. He decided, I wanted to try to figure out the mathematical odds for getting to this perfect middle spot when it comes to entropy. And so he did the math on how many options there are of high entropy universes that don't support life or sustain life, and he figured out the number of how many options there are with the opposite, and then he compared it to our own. And this was the number I've shown you before, but it's very important. Here's the number he came up with. He said, when it comes to configurations of the universe that do sustain life, he said there are 10 to the 10th, 10 to the 10th to the 101st options, okay? This is a very, very astronomically large number, right?
Yeah.
So it seems like, oh, there's a lot of options that support life. Then maybe it's not so far-fetched that it came about by chance. Well, the problem is he also configured the number for how many there are with regards to universes that don't sustain life. And this is the number he came up with. Now, does this number, it's 123. Do these numbers seem all that different to you?
Nah.
It looks small, but if you monitor it, it's a huge difference.
Yeah, here's the problem. It's hard to conceptualize these numbers, hard to visualize them, right? But this number, even though it's astronomically large, is a tiny, 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 tiny fraction of this number.
Yeah.
So, let me give you an example. If you divide this number by this number, you just get this number again.
What?
Because it's basically dividing it by 1. That's how small this number is in comparison to the other one. So, it's really hard to visualize this number, okay? But here's a good way of doing it. I've shown you this before too, but here we are. This is the number of particles estimated by astronomers that exist in the universe. Again, astronomically large. This number is so much larger that it has more zeros in it than there are particles in the universe.
Wow.
Yeah.
Okay, so in other words, if we were to try to write out this number with all the zeros, we would fill up the universe. Okay? That's how big this number is in comparison to this one. So, my point is, Penrose came up with the fraction of 1 out of this number. In other words, the odds, what are the odds of the entropy being set up the way it is?
1 in 10 to the 10th power of 120.
Yeah. In other words, practically speaking, impossible.
Wow.
So this is a very interesting thing. I'm going to combine it with number 3 now, okay? Fine-tuning of the expansion rate of the universe. So again, we're going back to this idea that the universe is expanding. We know that, of course. But what's interesting is that if the universe were expanding just slightly faster or just slightly slower, there would be no life. Yeah, life wouldn't have happened at all. So this number is a little bit better, but not really. Here's the number that's widely accepted by physicists and astronomers, okay? It's 1 out of, or 1 part in 10 to the 90th power.
Oh, it's a small number.
Oh, that's a small number, right? Okay. Remember the number of particles in the universe? 10 to the 80th power. Which means this number is 10 billion times more than 10 to the 8 than there are particles in the universe. 10 billion times more.
Whoa.
That's hard to even wrap our minds around. Think of it this way. the odds of the universe expanding at the rate it does when you compare it to all the other options of speed, right? The odds of that happening are fairly comparable to the odds of you putting on a blindfold, being able to teleport anywhere in the universe and picking out a particular particle that has writing on it and said, oh, you picked the right one. Okay, you won the lottery. Okay.
Whoa.
Only the fact is that the odds of this happening are 10 billion times less likely than that. Okay? So again, hard to put our mind around some of these numbers. But this is where the moment you get this high is the moment you're dealing with impossibilities, right? We can say, oh, there's a slight chance. But through all practical means, it is impossible. Okay? So that's the idea. The point is that when it comes to what's in our universe and how and the rate that it's expanding and the amount of disorder that's in it, all of these features are finely tuned for life. If any of them were slightly different, and I mean slightly, then there would be no life. Okay? So now let's zoom in to the Earth. And this is where we get into a little bit less hypothetical stuff, and we talk a lot more practical. Okay? So number 4.
Level of oxygen.
Oh, yeah.
Oxygen level on Earth. We're gonna shoot through these, okay? We're gonna shoot through them, okay? Oxygen level. Can anybody tell me how much, what the percentage of our atmosphere is oxygen? 21%. Very good. Okay, 21%. If it were slightly higher, at 25%, fires would erupt spontaneously. Okay?
Oh, yeah.
Out of nowhere. Because oxygen, of course, feeds fire.
Yes.
If it were lower, at 15%, human beings would suffocate. So again, it's right at the level it needs to be. We're going to have to shoot through. Second one, Earth's atmosphere. We've talked about this one. Some of you guys brought it up yesterday. So, what were some of the things that you guys brought up when it comes to atmosphere?
Ozone.
It destroys asteroids.
It destroys asteroids. You said the ozone?
Ozone layer. Or we would all become like, if you didn't have ozone layer, it would basically be like a giant microwave. We'd all die.
Yeah. So, the ozone layer keeps us secure for microwave radiation.
It would be a macro.
Microwave, excuse me. Okay. The degree of transparency of our atmosphere is also very important, and it's a necessary constant for life. If it were less transparent, ozone layer included, the solar radiation would kill us. It would bombard our surface. But if it were more transparent, we wouldn't be able to grow food and there'd be no life because we need the sun's nutrients in plants, right? We need that radiation. We at least need some degree of that radiation so that we can actually have food. And so here we are in a situation where, once again, it's perfectly balanced, where if it were slightly more, we would die, or slightly less, we would die. Same thing with water vapors, water vapor levels in the atmosphere. If the water vapor level were greater, we would all basically cook like we're in a boiling pot. Okay, you guys heard of the greenhouse effect and all that?
Yeah.
Okay, so if we had a higher level of water vapor in our atmosphere, the greenhouse effect would go rampant and we would die out.
Water vapor is good though on a smaller scale.
Exactly. If we had too little, what would happen?
This is what they use for, like, me, I have asthma, so they have a machine that they put liquid medicine in and it turns it into like a steam vapor.
Okay.
And like,
Yeah.
No, really any natural warming effect. It's not enough.
Yeah. So we need the greenhouse effect, but we don't need it to go off the rails and cook us all, right? There's got to be a balance. Okay. So again, we happen to be, and I use that term loosely, we happen to be on the planet with the perfect atmosphere. Okay. Same thing with number 6, Moon-Earth gravitational interaction. If the moon were closer, what would happen?
Tidal waves?
Yeah, tidal waves would make life impossible. Okay. Again, for those who've seen Interstellar.
Oh, when they're like in the middle of the
Yeah.
ocean and then they see like this huge wave
Yeah.
crash on there.
That's a result in the movie from the black hole being nearby, right? So same idea. If the moon were even slightly closer to our planet, our tidal waves would be going crazy, and there'd be no chance for life.
I think it should be close. You go to Pipeline, Hawaii, get 25 foot waves, and you go on the Steel Beach and like 2 feet.
I don't think we want that. And then if it were slightly further away, what would happen?
No waves.
No waves at all, and that's bad, right?
See,
We need our ocean currents.
It would be like, you'd have no current, no tide level, just be like completely
What,
stagnant.
all
Yeah, things would stagnate. The ocean life would die out. Okay, this is
auction or auction would die out.
yeah. So we need the currents in the water to oxygenate the water and to keep things living in the ocean. And if everything were to die in the ocean, would we live long?
Coral reefs produce more oxygen than trees.
Exactly.
Long?
Well, I think it's plankton, but I wouldn't look at that. But the point is, we get most of our oxygen from the ocean, ironically enough, from plankton and perhaps some coral reefs, but I think from plankton. The point is, we need our ocean to be healthy, and if it's not healthy, we die. Okay. So the moon keeps it healthy. This is one of those things that people who freak out about global warming and so on. This is one of the things that they point to. They say that too much cold water being melted into the ocean would mess up the ocean currents and would lead to all sorts of problems. Okay, weather patterns would change and so on. Okay, we're not going to get into global warming and all that, but that's just to prove the point of how important these ocean currents are. Yes.
In a non-fiction movie, a dude stole the moon. Would that be possible?
He would kill us all. Okay.
He condensed it. He put a shrink ray on it
and
We'd all die.
Oh yeah.
and we'd all die.
It'd still be just as like massive, like not big, but just as heavy. You can imagine. So just you have like
All right, if we could theoretically shrink things, you're right. Okay. Let's keep going. Number 7, carbon dioxide level. If CO2 levels were higher, what would happen?
We wouldn't be able to breathe.
We wouldn't be able to breathe. Also, the greenhouse effect would go rampant again. But if they were lower, what would happen?
They'd all die.
Why?
We wouldn't have trees.
Yeah, because plants need them, and they're what are providing us with oxygen. So this very delicate system, right, that of plants and humans, or plants and animals, okay?
Extremely delicate.
It's extremely delicate.
0.01 will die.
Yeah, of course, we need rain to keep the trees alive too. So we have carbon dioxide level. We also have gravity, which we've kind of brought up.
This girl Trisha Paytas on a
Imagine we did
podcast
have
said that she
gravity.
doesn't need it.
She doesn't need gravity.
She says that she claims that we don't need gravity, and also claims that Isaac Newton invented it
Yeah.
instead of discovering
Okay,
He's
word of advice: don't listen to people like that. Okay.
Yes.
Okay, here's what physicists and astronomers have come to realize about gravity. If it were slightly different, and I mean like the amount of force, the amount of force was slightly different
When the moon go
by an infinitesimal amount.
We'd be crushed to the ground.
Yes, but let's think bigger. Okay,
We would be like moon gravity, and we'd be able to jump really high.
Orbits off, all that stuff.
let's think bigger. Okay, think about the sun.
Yes.
If gravity were just off by an infinitesimal amount, the sun couldn't exist. And what would happen to us? Okay. We need stars in order to live. Okay, that's just one example when it comes to gravity. Again, the idea is that it is a delicate balance of many systems working together. Here's another one, the axial tilt of the Earth. This was brought up yesterday. This is what gives us seasons. It's what keeps the Earth, or different parts of the Earth, from freezing or heating up too much. The axial tilt is, again, just right. It's 23 degrees. And it is, again, just right. If it were to be altered only slightly, surface temperatures would become too extreme. It would be too hot in one corner and too cold in the other. Yes?
Isn't there still AX?
Yeah, that's what I said.
Is that a typo?
I believe it could be for like a different type of action.
I think that's accurate, but somebody Google it.
Wait, isn't that axis?
It's an axis, right?
Yeah.
Oh, you remember an axis and an axle?
Yeah.
Axle and axle.
Just on a tour.
Nice.
All right.
Yeah, it's not AXL.
So is it AXEL?
It's AXLE.
Oh. Are you sure?
Yes. You turn the air on, it's warm in here.
Yeah,
Sure.
okay.
I got something that we
Thank you.
That's my
Okay, so go ahead and spell out the AXLE. That's fine. We talked about this yesterday. What about Jupiter? Helps us.
Oh, it's marked all the asteroids.
Yeah.
So they come in and they like.
So its enormous gravitational well saves
throws them
us.
off.
Throws off asteroids. Again, think of gravity as Einstein did, like a giant trampoline, and different weighted objects are pushing it down, okay? So let's say we have a giant trampoline and we put the planets on it.
Well,
Okay?
Pluto.
You have one that's really big and it's drawing in all the other tennis balls and so on. And this little ball over here gets to be safe, right? So that's what Jupiter does for us. What was the question?
Oh, I was making a joke about Pluto.
Alright, never mind. Alright. The Earth's crust. This is an interesting one we don't ever hear about.
It's like pizza.
If the Earth's crust were greater, in other words, the thickness of it were greater, what would happen?
Sorry, what?
If the Earth's crust were thicker, what would happen?
Oh, no agriculture. You couldn't grow any plants.
Okay,
No?
it's a good theory. Here's the problem. Too much oxygen would be sucked into the ground,
Mm.
and we'd suffocate. No, we'd suffocate. Okay, but if it were thinner,
We would
just block off the
too
ground.
close and the ground too hot, right?
we wouldn't have come about. Is the point. We wouldn't be here at all. If the Earth's crust were a little bit thicker, we wouldn't be here at all.
What's all the chances that they believe in if it was already like fully paved?
What?
With all like the random like chances that they believe in, if they just say that what if the Earth was just
Well, that's the problem. That's what we're pointing out is that you've got so many of these systems that are delicate, right? And they're all perfectly in place. We're going to talk about some of the atheistic responses in a bit, or later, not today. Okay, but there are some responses that they give, but none of them are convincing to me at least. Okay, so Earth's crust. If it were thinner, what would happen?
No.
It'd be too hot.
Oh, too much oxygen.
Tectonic movement would be too.
Tectonic.
Too much oxygen and
Wait, what is lava?
We would have. Okay, here's the problem. We would all be in lava and die.
Yeah, we would all be
Okay,
lava and
there'd
die.
be too much volcanic activity, the ash in the air, things like that would make it unsustainable. Okay, same thing. Here's the final one, number 12. And again, this is just
Lightning and earthquakes.
I lumped them together because I didn't want to lose one and I didn't want more than 12. And because they're both similar in the sense of we think of lightning and we think of earthquakes as like bad things sometimes.
Yeah,
There's a video of like
Because they can hurt
far
us.
away. Like, wow, that's raining in like a certain spot.
nice.
Yeah.
Like you could see like how it like divides into like just one area.
Lightning's actually.
Oh yeah, you can see that.
Lightning can kill us.
So
Back in
here,
the car.
let me ask you this. What is lightning?
It is
It's
electricity.
high voltage
It's
and
like
losing
wow.
electricity.
You know, isn't it? Andrew, what
Well,
is lightning?
there's a
What is
lot
the
of
technical
names.
science definition? I
Okay, before we get into pagan idolatry. Okay, lightning is atmospheric discharge. Okay, it's a giant static shock. It's getting rid of this static charge and it's going into the ground. But here's the thing: if there were too much, if there was a little bit more lightning, what would happen?
We burn too much stuff and have too much electricity.
Yeah, we'd be frying. Okay.
Oh, what does it?
But if we had too little, you think anything would go wrong? You think life would be fine without lightning?
Oh,
Okay,
I wanna
you know what
happened.
happened.
I really want to know what happened.
So, if there were not enough lightning, too little nitrogen would fix in the soil.
Yeah.
So lightning actually helps bring nitrogen into our soil. Nitrogen, of course, is in the atmosphere. We need it in the soil to grow anything. Okay? So how do we bring one to the other? Lightning. So if we didn't have lightning, we wouldn't be able to grow food, we'd all die. Okay? Or we wouldn't be here at all.
Earthquakes. With the F.
Earthquakes. So let me ask you this one. How on earth could earthquakes actually help us?
I didn't think you did all those. I do lightning in the night.
By making mountains and stuff.
What?
No, they
Okay.
do.
So-
They go like this, and
so-
they create mountains.
Think of it as very similar to what I just think of it as very similar to what I just described with lightning. So we need nitrogen in the soil, lightning brings it down. There are also nutrients at the bottom of the ocean that can basically settle there at the bottom, and earthquakes actually stir them up and bring them up to the soil where we need them.
Those make mountains too, which gives you like.
Mountains are more from
That's not-
volcanic activity than they are from earth.
And if there is too many earthquakes, too much
How do you know this?
activity, we'd all die a little long and
Sorry?
right?
That is normal.
How do I know all this?
Because he looked it up and researched it.
I do a lot of research for this class, okay.
Are we your only class?
Yeah.
Yes.
Okay.
Okay.
So you would say.
Of course,
we're
I'm
the
a
best
preacher and I
class?
do other things.
Oh.
Go ahead. What was that?
So we're your favorite class then, right?
Oh yeah, you're my favorite and my least favorite at the same time.
We're the worst.
It's
Kinda like
Joseph's
that.
fault.
Kinda like that.
Okay, so real quick before, because you're about to go. Okay, listen. There's a guy named Fred Hoyle, an astronomer who was an atheist, who basically saw all of these conditions.
Sounds familiar.
He also saw one of the big things he said was carbon, which is one of the things I could have talked about, but didn't. The amount of carbon in the universe, which is very important. But anyway, here's something he said, because this really shook his atheism. He looked at all this and he thought, you know what? I can't really be an atheist any longer. He said, a common sense interpretation of the facts, common sense interpretation, suggests that a super intellect has monkeyed with physics as well as chemistry and biology, and that there are no blind forces worth speaking about in nature. So here's the point. The common sense interpretation of all of this data is that there is an intelligent mind behind it, right? That's the common sense reaction. To react in other ways and say that it's by chance, in my opinion, is to hold on to an ideology for which there is very little evidence. Does that make sense? Yeah.
Then it's just stupid.
Basically not, right.
Zero.
Okay, so tomorrow or Friday we'll talk about some of the atheistic reactions to all this. Okay, you can go.